Statics is a subset of physics which serves as the foundation for all engineering mechanics courses. Statics is an area of study that is restricted to particles and rigid bodies that have no movement. There is no acceleration. They also do not deform. So they're rigid bodies that do not bend, and they have no acceleration, and thus are static. Sir Isaac Newton established the foundation of mechanics in 1687. He formulated the three laws that describe the relationship between forces on an object and motion. And these three laws will be what we use to establish some of the basic equations and how we go about solving statics problems. To understand the three laws that Newton devised, we first have to understand the two types of motion that we're dealing with here. The first one is translation, where the bodies change position without changing orientation. In other words, they don't spin, they just move. Rotation is where the body spins but does not move. And of course, you can have combinations of these two forces acting on an object. So let's look at the first law that Newton came up with. So Newton's first law states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. In other words, an object's going to stay put unless you exert a force on it, and it's going to stay in motion unless you put on a force on it, a braking force or an opposing force. Newton's second law is stated as when an object is acted upon by a force, the time rate of change of its momentum equals the force. And this is where we come up with the foundational formula that we use in statics, which is F equals ma. Now, since we're dealing with statics, that means that there is no acceleration. Velocity is constant. So A is equal to 0, and this results in the basic equilibrium, which is the summation of forces is equal to 0. And is it how that we determine internal forces, external forces that act on an object. Newton's third law states that for every action, there's an equal and opposite reaction. And this we can see demonstrated in this figure here, where we have an object sitting on a table. Okay, it has a force of its weight acting on the table. The table also has its own force, which is the weight of the table itself. So those are forces acting on this system, but you need an opposing force. In this case, it's the pressure on the floor, which results in the table not moving. Okay, so you got the reactionary forces located at each of the legs on that table. To solve problems in statics, we have to quantify and put numbers with these problems. So we are needing to look at the units of measure that are used. So if we look at the units of measures for all of physics, we essentially have 7 of them. And from these 7, we will develop other ones. But these are the basic 7 ones you can measure. So you got length, mass, time, electrical current, temperature, the amount of a substance, and luminescence intensity. With statics, we're going to be concerned with length and mass. Now, with these, we can then further define them, such as velocity and acceleration, but they all are derived from length, mass, and time. So let's first talk about the systems we will be using in this course. The first one we will talk about is the International Systems of Units, SI. You know it as the metric system. And then the standard units that we used customarily in the US are called the US Customary Systems of Units, which is USCS. If we look at this table, this defines the actual units that are used for each one of these. So let's look at length. For the SI, it's meters, and for the USCS, it's feet. Time is the same for all of them, and mass is different. Mass for the metric or SI is kilograms, and for the USCS, it's slugs. Now, the line that I have drawn here represents the departure from our basic units of measure, length, time, and mass. And all the ones below are using the basic units of measurement above to construct them. So let's take a look at the first one. The first one is velocity, and it is derived by taking the length divided by time. And so you get the units of meters per second and feet per second. Acceleration is just another further derivation of this, and that's meters per second squared and feet per second squared. The unit of force is measured as in SI is newtons, and in US CS it's measured in pounds. Now, remember the formula that we had from Newton's second law. This was F is equal to ma. With this in mind, F is force, so 1 Newton is equal to mass times acceleration, which is meters per second squared. And if we take that same logic, but we're going to solve it for mass, 1 slug is equal to force divided by acceleration. It's also important to note that we are using different constants for gravity acceleration. Okay, G, which is gravity acceleration in SI, we're going to be using 9.81 meters per second squared. And for the USCS, we're going to be using 32.2 feet per second squared. It's also important to note that in the U.S. customary system units, that 12 inches is equal to 1 foot and 1 kip is equal to 1,000 pounds, as it is much more convenient to describe large forces with kips as opposed to pounds.